Welcome back, friends. In the previous lecture we have started our discussion about electric potential, and this electric potential we tried to understand that what is the relationship between electric potential and electric field intensity and potential difference VAB in terms of these things we have calculated. So finally we have got the equation VAB as VB minus VA, where VB is the absolute potential at any point B and VA is absolute potential at any point A. We also understood the concept of absolute potential, where the reference, if we are calculating a voltage at B, assuming that A is a reference point, and if A is as infinity, if we put RA equal to infinity, we get that voltage at point B, and that's the concept of absolute potential, and we got it as V equal to Q upon 4 pi epsilon R. Now if you can compare the equation of E bar with this voltage, see the first basic difference between E bar and V is a scalar entity and E bar is a vector entity. Another thing is potential is inversely proportional to R. If you can see, potential V is, if I assume Q upon 4 pi epsilon naught as a constant entity, V is inversely proportional to R. But if I want to calculate electric field intensity due to point charge, it is Q1 Q2 divided by 4 pi R square. So actually when I write this E bar is inversely proportional to R square, So it's better to deal with the potential as compared to the electric field intensity as well as solving mathematical expression is concerned. So it's better to deal with the electric potential. That's another advantage of understanding this potential. Finally we got the expression V equal to minus integration running from infinity to R E bar dot dl bar. And now today we'll see the next part of it. We have gone through those note or summary of that. Today we'll see the most important bit of the topic. This is a relationship between E bar and V. Now see, when we want to establish a relationship between E bar and V, see, V is a scalar entity, E bar is a vector entity, so there must be some mathematical expression which will correlate this E bar and V, and we'll try to understand this in this particular way. Now the potential difference between A and B, we already know that it is taken as VBA equal to minus VAB. We already know that if the potential difference VBA is exactly equal to V minus of VAB, and potential is independent of the part taken, that we understood. Now if we take this VAB on the left hand side, can I write VBA plus VAB equal to 0? Yes, I can write. So VBA plus VAB equal to 0. But we already know that potential difference, because this was the last expression which I told you that this is important. Potential difference is E bar dot dl bar. If you can see here also, potential difference VAB equal to minus A to B E bar dot dl bar. So that means E bar dot dl bar minus of E bar dot dl bar is also 0. That means closed line integral. See, this is a closed line integral. Closed line integral of E bar dot dl bar is also 0. So if it is 0, it shows that line integral of E bar along a closed path must be 0. What I mean to say, this concept also you might have studied. Work done around a closed path is always 0. If certain person starts at point A and reaches to a point B, or certain charge I will say, and he will come back by the another path, and if they forms a closed loop around this path, then total work done around a closed path is always 0, because this is a positive work done and this is a negative work done, or this is negative or positive. They will cancel with each other out, and finally I will get E bar dot dl bar equal to 0. So this shows that integral of E bar along a closed path must be 0. Physically it implies no net work done in moving a charge along a closed path in the electrostatic field. See, once again I will explain. Around a closed path in the electrostatic, whenever I am talking, total work done around a closed path is 0. So the work done, let's say this is W1, this will become minus W1. Work done is not negative, but potential difference is negative. So VAB minus VAB will turn out to be 0. And finally we get closed line integral E bar dot dl bar equal to 0. It means that no net work done. See, this is important. No net work is done in moving a charge in a closed path. So if that is so, we also understood a Stokes theorem while understanding the basic concepts of vector calculus. So we will apply here, applying Stokes theorem. Closed line integral of E bar dot dl bar, closed line integral of E bar dot dl bar equal to del cross E bar dot ds bar. So see, closed line form surface. I'll just explain you with one example. Let's say I am starting with this point. I will go rightward, then down, then left, and then up. So if I started drawing a line, I have closed a line. Is it visible as surface? Yes. So the closed line always forms open surface. See, this is not a closed surface, this is open surface. So del cross E bar dot ds bar equal to 0. Since E bar dot dl bar is equal to 0 according to Stokes theorem, del cross E bar dot ds bar should also be equal to 0, and therefore del cross E bar is also equal to 0, and this is the next important Maxwell's equation. So in the previous lecture we have gone through one Maxwell's equation, that del dot d bar equal to rho v according to Gauss law. This is the second Maxwell's equation that we will see in the point form and integral form, but right now del cross E bar is equal to 0. So any vector field that satisfies above equation is said to be conservative. What I mean to say, if curl is 0, you usually call that vector field as either conservative or irrotational, since curl is 0. So electrostatic field is a conservative field. Conservative field means it has source point and sink point. That means if it is a plus q point, then it will be radiating electric lines of forces. If it is minus q, it is accepting, or electric lines of forces will start from infinity and terminate on minus q. So it is having a conservative nature. Okay, so we can write dv now. See, I want to write differential volume as E bar dot dl bar. See, what was the differential potential dv. See, if I write v equal to closed line integral E bar dot dl bar. See, this is a basic equation. Can I differentiate on both sides? Yes, I can get dv equal to integration derivative get cancelled. It will be E bar dot dl bar. So same thing I did here. So it's not differential volume, it is a differential potential. dv equal to E bar dot dl bar. Minus sign stand as it is. Now if it is dl bar, you already notice in the vector notation that dl bar is a line integer, this is a line vector and will be represented by dxax bar plus dyy bar plus dzaz bar. So if I write this as E bar as exax bar, eyy bar plus ezaz bar, and dl bar as dxax bar plus dyy bar plus dzaz bar. So there will be a dot product between E bar and dx. So I will give ex, finally I will get minus ex dx minus ey dy minus ez dz. So you can do, just try this, write E bar as exax bar, eyy bar plus ezaz bar, and dl bar as dxax bar, dyy bar plus dzaz bar. You will get finally this expression. Now what I am going to do, but dv, already we know that if I am talking about a voltage, it is a partial differentiation of v with respect to x. See, this is the formula for dv. This is you might have gone through in the mathematics. Even we have talked about this in the previous lecture when we have talked in the vector calculus. So dv is equal to dou v by dou x. Usually we call this as da by y, da by x, or whatever it may be. I usually call it as dou v by dou x dx plus dou v by dy dou y dy plus dou v by dou z dz. So if we can compare these two expressions, the expression for dv here and expression for dv here, what I will get? I'll just get ex as minus dou v by dou x, ey as minus dou v by dou y, and ez as minus dou v by dou z. And if I can find the expression between them, E bar is equal to minus grad v. See, this is most important expression in the examination point of view. Sometimes it will be asked like directly that derive the expression between E bar and v, or it will be asked give E bar as minus grad v. So there is no dot between them, there is no cross between them. We already studied that gradient is a point of maximum slope. So E bar is equal to minus grad v. So the slope of maximum potential on the curve can be represented as E bar. So E bar is equal to minus gradient of v, or we'll call it as E bar equal to minus grad v in simple words. And now relationship between E bar, that is electric field intensity is a gradient of v, that you already know. The negative sign shows that the direction of E is opposite in the direction of which v increases. E is directed from higher to lower levels of v. That means if I want to draw the curve of v and E, so they will be going in the opposite direction. Equation shows another way to obtain E bar field apart for using Coulomb's law and Gauss law. We already noticed E bar by using Coulomb's law and Gauss law. So potentially if I want to calculate E bar and potential is known to me, this is the easiest way to calculate E bar. If a potential V is known, E can be found using previous equation. The previous equation is this equation. So if V is known to me, I can calculate E bar by using this expression. So there are now 2 or 3 formulas for calculation of E bar. One by using Coulomb's law, one by using Gauss law and another by using this potential expression. So these all 3 points are important in the examination point of view. So just go through it, try to understand the basics, and try to write it down once, and so that this concept will be clear, more and more clear to you. Okay, so that's all from my side. So I will stop here. Thank you for patient listening. Happy learning. Thank you very much.